Buffering capacity is the amount of acid or base that a buffer can absorb without a significant change in pH. The greater the concentrations of your acid and base, the larger the capacity. The greater ability it has to absorb acid or base without changing its pH. So in this problem, we are adding 0.01 moles of HCl to a 1 liter buffered solution of 5 molarity acetic acid and 5 molarity of sodium acetate. First thing you need to do is figure out what the HCl is going to react with. We have acetic acid and sodium acetate, which is its salt, which is a base. So the HCl should react with the base of sodium acetate. You can ignore the chlorine as well as the sodium since they're both spectators. And then you're going to need to do stoichiometry. Remember, in order for that, you're going to need moles of each substance. So we have 0.01 moles, 5 moles, and 5 moles. Getting 5 moles from 5 molarity times 1 liter. React to completion. And that should be 4.9 and 5.1 are 5.99 and 5.01 moles. We're left with a buffer, so we can use our Henderson-Hasselbalch equation. pH is equal to pKa, which is 4.74, times log of our base, which should be 4.99. That's a mess up. 4.99 and 5.01 being our acid. So pH should equal 4.74. And so our change in pH would be 0. Okay, same exact problem, except we're starting with 0.05 molarity of acetic acid and sodium acetate. You have moles of each thing. React to completion. And again, we're going to be left with our buffer. Make sure you divide by total volume. Just get in the habit of doing that, even though it's 1 liter. And use Henderson-Hasselbalch again. So pH is equal to 4.74. plus log of 0.04 over 0.06. And our pH before we add the acid is 4.74 since our acid and base concentration are equal. So log of 1 is 0. So pH equals pKa. So our pH is 4.56. We could get the change by subtracting the two. I'm going to try this one on your own and restart once you have your answer. The answer should have been negative 0.18 since that was the change in pH. We have HCl being added to a buffer. So you need to figure out what the HCl is going to react with. In this case, it's going to react with the sodium fluoride. You need moles of each thing. So that's 1 times 0.004. Which gives us 0.004 moles of acid. And then we have 0.2 molarity and 0.1 liters of buffer. So that's 0.2 moles of HF and F ion. Plug those in. React to completion. Make sure you divide by total volume. So that's 100 plus 4, which is 104 milliliters or 0.104 liters. That's going to give us 0.154 molarity and 0.231 molarity. We have a buffer, so we need to use Henderson-Hasselbalch. Our pKa is 3.14. That's the pH that we started with. So pKa plus log of our base, which is 0.154, over acid, which is 0.231. So pH is equal to 2.96, which is a difference of 0.18. Go ahead and try this one. The Ka is 1 times 10 to the negative 10th. Since we're looking for the change, we need to find our initial. Again, our concentrations of acid and base are the same. So pH equals pKa because log of 1 is 0. So that's our starting pH. We're adding NaOH. So the NaOH is going to react with the HCN, which is our acid. You can leave off the sodium. We need moles of each substance. So 0.8 times 0.004 gives us 0.0032. And 0.2 times 0.130 gives us 0.026. We can ignore water. React to completion. We get 0.0228 and 0.0292. We're left with a buffer, so we can do Henderson-Hasselbalch. But what did I forget to do there? I'm left with moles, not molarity. So I need to go back and find my molarity by dividing by total volume, which in this case is 134 milliliters, or 0.134 liters. Okay, and that's not quite right. My concentration of base is 0.218, and my concentration of acid is 0.170. Plugging that in, my pH is now 10.11, which is a change of pH of 0.11. Alright, finally, choosing the correct buffer, the ratio of acid to base should be as close to 1 as possible, and the pKa of the acid should be as close to the desired pH as possible. So here we want to make a pH of 4.3 buffer, and we have 4 acids to choose from. Well, the first thing we want is a pH a pKa close to the desired pH. So find your pKa's for each of those. Looking at that, we can eliminate A and D because their pKa's are quite far from our desired pH of 4.3. Now we need to find the ratio of acid to base that would work and give us a pH of 4.3. Because if we had a 1-to-1 ratio, we would have a pH of 4.89 and 4.19, which is not what we wanted. So in B, we want a pH of 4.3. We have a pKa of 4.89 plus log of base over acid. So we're using Henderson-Hasselbalch and just solving for base over acid. So subtract 4.89 and then raise it to the power of 10. So your base over acid should be 0.257. Do the same thing for C. This time your ratio is 1.29. So C is closest to 1, so that's our better buffer. But we want the ratio of acid to base. So we need to do the reciprocal, or 1 over 1.29, to get that ratio. Which is 0.78. Make sure you know what that means. That's 0.78 molarity acid and 1 molarity base.